Welcome to Python tutorial 4 of the course Time Dependent Quantum Chemistry. In this tutorial, Python tutorial, we will learn how to represent a matrix in Python programming, and then subsequently how to calculate eigenvalues and eigenvector corresponding to that matrix. With the help of this tutorial, we will be able to learn how to numerically calculate stationary states of a quantum system, stationary state wave function and stationary state energies of for a quantum system. Technically, we are actually exploring we'll be exploring the eigenvectors and eigenvalues associated with a particular Hamiltonian. So, we are solving time independent Schrodinger equation. So, we will take a look at it with what is the procedure to represent a matrix in Python programming. In module 4 of this course, we have already realized that mathematical language of quantum mechanics is linear algebra. That we have already realized. And in addition to that, in the same module where we have shown the connection between the quantum mechanics and linear algebra, we have presented the grid representation of the wave function. So, we said that the entire space can be divided into equally spaced grid, and the wave function will be represented as a discretized function on this grid like this. So, within this grid representation and using finite difference method and within the boundary condition, we have to use the boundary condition. Boundary condition, it means that the wave function value would be 0 at these boundaries of the grid. So, where the grid will be terminated in theoretically the wave function should be extending from minus infinity to plus infinity, but we cannot take such a infinite boundary grid in computation. So, we make it a finite boundary, assuming that at the boundary the wave function takes 0 values. So, we use this boundary condition, then finite difference method for the derivative and the discretized wave function. Then what we get is that this is the kinetic energy operator of the kinetic energy part of the Hamiltonian. That kinetic energy part of the Hamiltonian can be expressed in terms of a matrix form like this. This is a tridiagonal matrix, that we have already seen it. And this delta x is the difference between the grid points. This is the adjacent grid points, and h cut m comes spontaneously directly from the definition of the kinetic energy operator. On the other hand, the potential energy part, what we have seen that it construct the it can also be represented in the matrix form, and it gives me the diagonal matrix. So, potential energy is a diagonal matrix, kinetic energy is a tridiagonal matrix, and if we add them together we get the total Hamiltonian. The Hamiltonian is nothing but the potential part and the kinetic energy part that we have seen. So, if I have the Hamiltonian and that can be represented in terms of matrix form, then we can immediately get the eigenvalue and eigenvector from that matrix. So, we have also realized in the same module 4 of this course where we have shown the connection between linear algebra and quantum mechanics, we have also realized that the eigenvalues and eigenvectors of a quantum system can be easily obtained by diagonalizing the Hamiltonian matrix. So, I have shown how to get the Hamiltonian matrix. Hamiltonian matrix will be obtained from adding these two matrices. Once we get this total Hamiltonian matrix in the grid representation, we are following the grid representation, which is nothing but pseudo-spectral representation of the wave function. And so, once we get the Hamiltonian matrix, then we can diagonalize the Hamiltonian matrix to obtain the eigenvalue and eigenvectors. And eigenvalues and eigenvectors are the spectrum of the quantum system. So, if it is a one-dimensional box problem, then I have this is ground state, then excited state, and then all the states can be explored, and each state are actually corresponding to eigenvector and eigenvalues of the particular Hamiltonian representing the quantum system. So, we get the entire spectrum, or we get the stationary states of the quantum system. That is why diagonalization process is very important in quantum mechanics. And how do we diagonalize it? In module 4, we have shown that diagonalization of a matrix, let us say I have a matrix A. So, in general, operator is shown like this way with a hat on it, and matrix is with the double line. So, if I have a matrix A like Hamiltonian matrix, then I can perform a linear transformation like this with the help of this unitary operator. This unitary operator has to be found, and if we perform this, then what will happen? The role of this unitary operator is that it transforms the matrix into a new diagonal form. This is a diagonal form of the matrix in which the diagonal elements represent the eigenvalues of the matrix A, and columns of the matrix U represents the eigenvector of the matrix A. So, all eigenvectors will be clubbed inside this unitary matrix U, and corresponding eigenvalues or eigenstate energies will be given in this diagonal matrix, which is lambda. So, all information will be just clubbed together, arranged together in these two matrices. And if we perform this unitary matrix, what is the origin of this unitary matrix we have studied already. So, if we perform this unitary transformation, linear transformation, then we get this diagonal form, diagonalize the matrix, and we get eigenvalues and eigenvectors. As an example, we have shown that we took a matrix A like this 2 1. This was the exercise we have done already, 1 2. This was the, let us say as an example we took it, this was the matrix, and 2 by 2 matrix, and for this matrix, in order to diagonalize this matrix, we actually got this this matrix U matrix, unitary matrix, as 1 by square root minus 1 by square root 1 by square root minus 1 by square root. So, this was the unitary matrix. So, if we diagonalize it, immediately this lambda we get as 1 0 0 3. So, one of the eigenvalues would be 1, another eigenvalue would be 3, and corresponding eigenvectors are 1 by square root this column, and another eigenvector would be this column. So, this is the way we get that, and we have analytically shown how to get that, but in this tutorial we will check it numerically using Python programming. In general, the data structure which is used to present a mathematical matrix in computer programming is called an array. So, in order to represent this matrix in computer programming, we need to use this matrix. If we want to represent, then we need to use an array. We need to put them in array. So, this is the structure we will use, array structure to represent a matrix. An array can be n dimensional, but 2-dimensional array is called a matrix and a 1-dimensional array called a vector. So, these are if we represent each column, then this is going to be a vector each column, and 2-dimensional array which is n by n matrix we are presenting here is this 2 by 2 matrix. So, it is a two-dimensional array is called the matrix. Python does not have any intrinsic or built-in functionality to deal with arrays. So, Python cannot be directly used. We have to use its submodule, that is called SciPy, which is scientific, which is prepared, which is built to perform scientific computation with Python. So, we have to use that submodule to deal with the array and different numerical linear algebra techniques or routines we have to use from the functionalities of SciPy. So, we have to to write down, to represent this matrix in Python, we have to import SciPy and then represent in terms of array, and remaining eigenvalue problem solving for to find out the eigenvalues and eigenvectors, we have to use this SciPy dot linear algebra submodule, which is expressed as SciPy dot linalg. So, this submodule will be used to find out the eigenvalues and eigenvectors. All features of SciPy linear algebra submodule, one can actually look up the features in the SciPy documentation, and all the routines are available in the SciPy linear algebra submodule. This SciPy dot linear algebra submodule is optimized linear algebra routine than NumPy linear algebra submodule, and that is why we are not using NumPy module here. We will just keep using this SciPy submodule of Python. And one more information can be useful to note down here is that the linear algebra submodule of SciPy has a direct interface with the Fortran LAPACK library, which is very efficient and faster for and most optimized linear algebra package developed in Fortran for several decades. So, that has an interface, and that is why it is more efficient. So, we will use this linear algebra submodule of SciPy to represent the matrix and to perform this to calculate this eigenvalue and eigenvectors. So, how to find out eigenvalues and eigenvectors? First, we have to represent the matrix. So, there are several approaches available currently in a SciPy linear algebra submodule to find out eigenvalues and eigenvectors of a square matrix. However, here we will follow these steps. There are many other ways one can do that, but we'll consistently use this step to represent a matrix and then find out the eigenvalue, eigenvectors of that matrix. So, what are the steps we are going to follow? First, we have to create an n by n square null matrix. This is something which you should remember. The first will create the null matrix. Null matrix is the matrix where we have all elements 0. So, this is I am writing 3 by 3 matrix where all elements are 0. So, we will prepare the null matrix first. So, we will prepare the null array first of the same dimension 3 by 3. Then we will replace or reassign the elements by desired value to create the final matrix. So, if I have to create this matrix, let us say 2 1 1 2, this is the matrix we have to create. So, then first we have to do a 2 by 2 null matrix. We will prepare the null matrix first, 2 by 2, and then we will replace each element value. So we'll instruct the program to replace the individual element like this way after creating the null matrix 1, and then this is going to be 2. And then once we have constructed the desired matrix, we can find out the eigenvalue and eigenvectors by simply this functionality, EIG functionality. What we do in EIG functionality, we can just simply write down EIG within bracket. If I name this matrix to be A, the array to be A, then I will get this. So E comma V, this is the energy, and the eigenvector, eigenvalues and eigenvectors will be given within this construct. It's a very simple way to do. In the background, linear algebra package or submodule of SciPy will be performing all the numerical task for me, and then it will give me finally this values and the vectors using this functionality. It's very simple to do. So we'll take a look at it, how to represent it. We'll go back to the laptop right now, and we'll try to construct the matrix. So first, as I have mentioned, I have to first construct the null matrix, and to construct the null matrix, what we have to do is that from SciPy we will import one functionality called zeros. So the zeros will be producing the array with every element will be 0, and then I'll name A as zeros within bracket. Now I have to define the matrix dimension. I want to perform matrix 2 by 2. So 2 comma 2 is my matrix dimension. So what it does, it immediately creates. So if I go back to the slide, so it constructs 2 by 2 null matrix first. So 2 by 2 null matrix, it means that these zeros will give me 0 0 0 0. That's exactly what it's going to create. So we'll prove that it is what is going to create. I will go back to the laptop, and I will now print this A. So I have created a null matrix, and I'll write down some instructions here which will be helpful. With a hash character, a 2 by 2 null matrix is constructed, because the final matrix which I am going to create is going to be 2 by 2, and here I will write down zeros functionality is imported from SciPy SciPy module. And I save that with the name test1.py. It is already saved, and now I would like to run the program. If I run the program, what we see here is that this is the way Python will show the matrix or the array. In Python programming we will call it array, but when in mathematical language it is the matrix. So in computer language we do not call it matrix. So what we are seeing here is that we can create, if we go back to the slide right now, we can create this 0 0 0 0 matrix very easily with the help of this zeros functionality. In the zeros functionality, remember that we are using a comma here to separate the to show the dimension, and we have double bracket here, one bracket for the zeros and another bracket for the to show the dimension of the matrix. So these are the two things which you should remember. We should not get confused by the notation. An array data structure can be created using this built-in functionality of SciPy, and Python's module SciPy has several functionalities to define an array of any dimension. For an example, these zeros, more specifically, the actual functionality is like this: zeros, then within bracket n comma n, then comma d type, that is called data type. This is the actual functionality where we haven't used this option, data type option, because this data type option, d type option is optional, and that's why we haven't used it. But if we use that, then it is actually defining what kind of data type I need. Is a floating data type or integer data type, we can define it. But I am not using it, and that's why, because it's an optional functionality, I am not using it here. Next, what we will do now, or according to the steps we have given, once we have created the null matrix of the same dimension, so this is the matrix we would like to first represent and then find out its eigenvalues and eigenvectors. Next step would be to replace the elements to construct the target matrix. So we have constructed the null matrix first, and then we have to replace it. For the replacement, when A represents, if A represents a n by n array, if A representing n by n array, then A, this construct A I comma j, this construct represents the ith the element of ith row and jth column. Of that array. So if it is so, then one can take some examples. Let's say, and these are indices, and we know that indices will start from 0. It will start from 0, then 1, then 2, like this way it will go. So A00, this index, this construct will give me, it will return the element in the first row and first column, which means first row first column element is this one. So that one I am going to assign. Then if I write down A 1 2, it means it is first row and second column. So this is the first row and second column. So this is going to be this one, and so on. This is just the way we are going to assign. So if we look at this, it is very simple to do, and similar assignment we have used for the list indexing. We have already seen that the Python's built-in list indexing is similar kind, but here we have to just show the entire dimension for this, because it is a two-dimensional. So we have to give each element, each index corresponding to that particular element. So what we are doing here is that first we have constructed the zero matrix, null matrix, and then individual element are reassigned now. So A00 is corresponding to the first row first column, A01 is the first row and sorry, this is A1 2, it means it is going to be second row and third column. Zero zero is the first row, first column. 1 2 is the second row and third column. So similarly, A01 now it's going to be first row, second column. So that is going to be first row and second column. Column is here, so it is going to be here, this one. Then 1 0 second row, first column, this one, and A11 is going to be second row, second column, this value, and that's the way we have assigned. We are reassigning it, and if we print it, we'll be able to see what we have assigned. So let's go back to the laptop and find out how to do that. So I'm going to now assign individual values. I'm going to assign it like this way. I have created the 0 null matrix, and then A, then 0 comma 0 is going to be now 2. Then I have 0 1 is going to be 1. Then 1 0, this is going to be 1, and then 1 1 is going to be 2. And if I print A, I'll be able to see what I have constructed. What I have constructed is 2 1 1 2. That's the matrix which we have constructed. So I'll go back to the slide. So I have constructed now this entire matrix, and the way Python shows it with the help of this arrays, this matrix will be represented in Python with the help of this double brackets. And we have constructed the matrix right now. On this note, I'll just mention one thing, that if I write down A this colon, then comma J, or if I write down A I comma this colon, it means that this will return me the entire jth column. So if it is let's say 0, then I will get back the entire column, and the entire column is going to be now 2 1. Similarly, if this is going to give me entire row, and if it is 0 comma colon, it means that I'm going to get back the entire row, and that is going to be 2 1, the first row, and this is first column because 0th index is indicating the first column. So these are the ways one can collect the particular entire row and entire column of a matrix which has been represented in the Python already. So we'll move on and we'll go to the third step, which is very important step, finding the eigenvalues and eigenvectors of that created matrix. So as we see that from here to here is now known, I have created the matrix. Then after that I am giving a name. The first one is the eigenvalue, second one is the eigenvector. And if I give the name with a separated by a comma, then it calculates the eigenvalue eigenvector of the matrix which has been formed. Here A matrix has been constructed with the help of this EIG bracket construct. So we'll print then E and V, and we'll see how they are printing. So we have already constructed, we'll go back to the laptop right now, and we have already constructed A. Now we will do one thing. I do not need to print it again because I know what I have created here, constructed here. I'll just go ahead with this E comma V. One can change the name and make it anything. Eigen values, and one can name it eigenvector. So any name is possible, but both has to be separated by comma, and the first one has to be eigenvalue and the second one has to be eigenvector. Then this construct EIG A. This construct EIG within bracket A, this construct is indicating that Python has to explore, find out the eigenvalue and eigenvectors. But before we do so, I have to import this feature from a SciPy linear algebra submodule. It is not available with SciPy directly, it is available with SciPy linear algebra submodule because it is a linear algebra routine which will be following. So it is going to be SciPy dot linear ALG. I am going to import, and then I am going to print E and V, print E, print V. Do not use capital letter in print because Python will not be able to recognize. It is sensitive to them, to the letters. So now I'll run this program. So if I run the program, what I see is that the first, it's printing two different arrays. It's printing two different arrays. The first array is this one, and the second one is printing like this. So E, the eigenvalues are given in an array. The first eigenvalue, I'll go back to the slide. The first eigenvalue is given by this. This is J is the complex number, what we express as I in mathematics, Python will express as J. So, and 0 multiplied by J means it is a real number. It is actually showing, by default it is showing in the complex form. So the first value, eigenvalue, is going to be 3, which means that E1 is going to be 3 and E2 another eigenvalue is going to be 1. This is going to be 1. So these are the two eigenvalues we get, and this is exactly we have found analytically. When we did this analytical solution, we have found it that this matrix has two different eigenvalues. One is 3 and another one was 1, and we have discussed these things in module 4 of this course already. So numerically we are finding the same results, and corresponding to the eigenvalues, what we have found, we are seeing that this eigenvector is presented in terms of in the again array form. This is another array which has been given. So these vectors are given in the array, and what it does actually, this construct E comma V equals EIGA, this construct computes the eigenvalues and normalized, it gives me normalized right eigen vectors. It gives me normalized right eigenvectors. So right eigenvectors, what does it mean? I have an operator acting on psi, I get eigenvalue and multiplied by the eigenfunction, the eigenvector. So this is called right eigenvector. Another expression I can have where A is acting from the right. This can also give me an eigenvalue equation. When it does that, then this is called left eigenvector. So by default, if I don't mention anything, so actual construct of this evaluating eigenvalues is following. This is going to be, this should be EIG, then name of the matrix, then we have to write left equals false and right equals true. That we have to write down, false or true. So generally by default it's taking right as true. If I need to get specifically left eigenvector, then I have to write down left equals true, then only I'll be able to get that. So if I don't mention anything, by default it's giving me the right eigenvector, and it is normalized form. So normalized form, and what we have got here is the normalized this is one vector, another vector is this one. So there are two eigenvectors we have which is clubbed together in this array. So now this construct actually giving me normalized right eigenvectors, and one can access the values of the eigenvectors like this because it is an array, and one can also access the normalized right eigenvectors in the matrix form in which jth column corresponds to the normalized right eigenvector associated with jth eigenvalue. So if the jth eigenvalue, if the jth eigenvalue is this one, then to get the eigenvector, so this is the eigenvalue, and corresponding eigenvector is going to be, it has to be represented like this way, colon comma j. So actually I am taking the column. So this particular column is associated with this eigenvalue, and this particular column is associated with this eigenvalue. This is the way they are representing. So if I need to pick up the eigenvector corresponding to a particular eigenvalue, then I have to pick up following this way. V has all the information hidden. I have to just pull up the particular column corresponding to that particular eigenvalue. We will now move on, and we will check what we have said right now particularly. So we have already calculated these things. So what we'll do, we will continue this session in the next class.